we have already derived the expression for the energy of the oscillator and the number of oscillators in a cavity. Now we will derive the expression for average energy of an oscillator. That is given by the equation average energy E bar is equal to E by N, and we are substituting the value of E and N that we have already derived. That is E is equal to N0 epsilon e raised to minus epsilon by kt by 1 minus e raised to minus epsilon kt the whole square, and N is equal to N0 by 1 minus e raised to minus epsilon by kt. And substituting and simplifying the equation, the average energy E bar is given as epsilon e raised to minus epsilon by kt by 1 minus e raised to minus epsilon by kt. We can further simplify the equation by dividing the equation with e raised to minus epsilon kt, both the denominator and numerator, and we are getting average energy E bar is equal to epsilon by 1 by e raised to minus epsilon kt minus 1, and 1 by e raised to minus epsilon kt can be written as e raised to epsilon by kt. So average energy is equal to epsilon by e raised to epsilon kt, epsilon by kt minus 1. And you know that from the Planck's theory, epsilon is equal to h nu. Therefore, the average energy of the oscillator can be written as, instead of epsilon we are putting h nu, so h nu by e raised to h nu by kt minus 1. So we have derived the average energy of an oscillator as E bar is equal to h nu by e raised to h nu by kt minus 1. But this is only the average energy of an oscillator. In order to know the energy density of radiation in the range nu and nu plus nu, nu and nu plus d nu, very small region, we have to multiply this average energy with the number of oscillations per unit volume in the cavity in the frequency range nu and nu plus d nu, which is called the density of states. And this is given by another big derivation, and it is equal to n nu d nu is equal to 8 pi nu square d nu by c cube. So by multiplying this density of state with the average energy of an oscillator, the energy density of radiation in the range nu and nu plus d nu is given as u nu d nu is equal to 8 pi nu square d nu by c cube into h nu divided by e raised to h nu by kt minus 1. And this equation is known as Planck's distribution law. Now let us see what is the total energy density of the black body at a temperature T. For that we are considering the energy density of black body between nu and nu plus d nu, which is given by the equation number 10. U nu d nu is equal to 8 pi nu square d nu by c cube into h nu by e raised to h nu by kt minus 1. This can be simplified as 8 pi h nu cube d nu by c cube into e raised to h nu by kt minus 1. And this is called the Planck's distribution law, and this agrees well with the experimental curve in the whole range of frequency of the black body spectrum. in order to find out the total energy density of black body at a particular temperature T, we have to integrate the above equation from 0 to infinity. So the total energy density U can be written as integral 0 to infinity du u nu d nu, which is equal to integral 0 to infinity 8 pi h nu cube by c cube d nu by e raised to h nu by kt minus 1. So we are employing contour integration in order to evaluate the integral that you have not to derive actually, but you should remember the result. That is, the total energy density U is equal to 8 pi raised to 5 k raised to 4 t raised to 4 divided by 15 h cube c cube, which can be written as a constant k into t raised to 4. And this is equation number 11, and this equation number 11 found to be resembles with the Stefan's-Boltzmann law. Boltzmann law says that the power radiated per unit area by a black body is proportional to the fourth power of the absolute temperature. Now let us check the validity of the two classical theory, that is the Rayleigh-Jeans law, which holds good in the low frequency range, as well as the Wien's law, which holds good in the higher frequency range. For that we are considering the Planck's distribution law, that is u nu d nu is equal to 8 pi h nu cube by c cube d nu by e raised to h nu by kt minus 1. Now considering low frequency, then h nu by kt is very small comparing with the 1. Therefore, you know that e raised to x is equal to 1 plus x by x plus x square by 2 factorial plus x cube by 3 factorial plus etc. Similarly, e raised to h nu by kt can be expanded as 1 plus h nu by kt plus h nu by kt the whole square plus etc. Since the h nu by kt is a very small value, we can limit the expansion up to 2 terms. So e raised to h nu by kt in this case can be taken as 1 plus h nu by kt. Therefore, the above equation became u nu d nu is equal to 8 pi h nu cube by c cube into d nu divided by 1 plus h nu by kt minus 1. Cancelling 1 and minus 1, we can simplify the equation as 8 pi kt nu square d nu by c cube, which is already given as the Rayleigh-Jeans law. Now let us see what happens when the frequency is very high. At very high frequency range, h nu by kt is very greater comparing with the 1. So e raised to h nu by kt minus 1 can be approximately considered as e raised to h nu by kt. So if you are putting that particular case in the above equation number 10, the total energy density u nu d nu is given as 8 pi h nu cube by c cube d nu divided by e raised to h nu by kt. And this can be simplified as 8 pi h nu cube e raised to minus h nu by kt d nu by c cube, which is known as Wien's law. So this success of Planck's hypothesis to explain the black body radiation in the entire frequency range leads to the beginning of new branch of physics called quantum mechanics. And also the Max Planck received Nobel Prize in physics in 1918 for quantum hypothesis. This is the most important thing you should remember.